Okay, sorry. Okay, still a minute. We're gonna give it a couple of minutes while we get still setting up. We're a bit early, so it's got some new equipment now. I've just seen. Okay, let's go ahead and get started. So welcome back. I'm not sure if, there's some people waiting. Let's see. But as I said, I'm gonna be doing this every week, whether there's a big crowd or just a couple of people. And actually, this is also part of my more, I wouldn't say recent, but it's been a few years where I've realized it's actually much better for me, sort of emotionally and mentally, to commit to a certain amount of time for projects rather than specific outcomes. And so I obviously am still interested in outcomes, but I commit to working on this project for 1 hour a week, and plus or minus a little bit of change. But this means that as a commitment, it's manageable. It's clear what it is, and there's really no risk of it ballooning. As opposed to when I commit to a particular outcome, then it's much more possible that maybe that's going to take a lot longer than I expect. And obviously we are often optimistic, but often it's just very unpredictable. So in this case, I am really just committing to working on this project once a week, for an hour, Tuesday mornings, or at least my mornings, and then I'm gonna go over. Then I'll do a quick recap, and that's it. Actually, the other day I thought about something for this project that I decided then to not do because I won't work on it outside of the working hours. Okay, so I'm gonna assume you see my screen. Okay, so there's still something there. I'm gonna actually it's a little bit bigger, and as part of the idea of this is also that part of the idea of this is also that I want to dog food our own products, our own data, and this is one of the principles we have, and I'm going to post something in the chat as well. So this is about the fact that we produce things for others, and it's important for me that we also use them internally, because that is what enables us to find to improve the things that we are doing for others, basically. Okay, and so as part of that, last time I showed you that we were working with a data set that we've published that was called rCompare, and this is actually publicly available as well, rCompare. And as I was working on this, I realized that the public version only had data for the ARG, and in fact we have internally computed a lot more, and so as part of as part of this, yesterday, and I've also posted on the EOS mailing list, I uploaded all of the other internal data that we had. So maybe I'll spend a few minutes here today as well, just describing what these data are, which is, so we have the GMGC, V1 version 1, GMGC Global Microbial Gene Catalog, and so sometimes if I'm looking away, I am seeing that I'm just checking the chat, so I see actually that there's a, and I'm checking both the YouTube chat and the Discord chat. So I saw that we didn't have annotations for, we only have the deep ARG annotations, and what these are annotations of all of the samples that are members of the GMGC V1 annotated with different tools. So and actually, so here we have, and one of the tools, it being Abricate, you can choose the database that we use. So we have Abricate with Argonaut, with CARD, with MegaRes, with NCBI, ResFinder, and ResFinder FG2, and then DeepARG and RGI. RGI is actually the tool that comes with the CARD database, which is one of the, so the CARD database is so you can use the CARD database here through Abricate, or you can use it through their own tool, and you're using the same internal database, but externally it's a different, or the way you're using the same database to annotate, but the process by which you annotate genes is different. So, and in this case, and this will be part of a, this will eventually be part of a manuscript that actually Svetlana is leading, which will also compare these methods, but it will also, so what we did here is we did this a two-step process. So first step, annotating the genes in the GMGC, so the unigenes, and then because we have abundances for these unigenes, then we can project one versus the other. So if we know that a particular unigene, unigene 123 is a beta-lactamase, and that unigene is present in samples, ABC, then we're going to say that in that beta-lactamase it's going to be all present in samples ABC. Alright, so going back to the so this is why, okay, so here this is why last time, and this was a question that Svetlana asked in the Discord chat, is why did we use DeepARG? And it's basically because that was the only thing that was available, and unfortunately, well, not unfortunately, there's nothing particularly wrong with DeepARG. It's a perfectly acceptable method. It's a slightly it's a method that's optimized for discovery, for returning a lot of results, as opposed to other methods that are much more conservative and who are optimized for only returning those instances where we can be really sure that this is an antibiotic resistance gene, and which one of these things makes the most sense to you is really then going to be very project dependent. And actually part of Svetlana's paper will be also quantifying and describing these differences, because we know that the results are different, but trying to give also some intuition. Right, so with all of that said, let's see where we were. Alright, so okay. Okay, and alright, so and here I said this before, let me make this a bit bigger. Alright, so I'm just going to rerun what we had before. And here. Okay, and we have, so this was with this was with deep ARG. This is what we saw before. Just quick recap. So working here I'm using NeoVim, and I have this setup, and maybe I'll also post on the mailing list the exact setup that I'm using, whereby so here's the file. This is the standard file, so I can save it, but I can also execute it line by line. And I think people are very familiar with this type of setup from tools like Jupyter or RStudio or or Visual Code, etc. But I'm a little bit old-fashioned, so I'm using it here in NeoVim. But you have everything that's present in this modern database or in these modern IDEs. Right. So read the CSV file. We're using polars. So question also came up. Why polars? I think it's a little bit. It's supposedly Svetlana was commenting on the Discord. Yes, it is supposedly faster than pandas, but to some extent, I really just wanted to try it out. If it might, it might turn out that it's just not good enough, or it might turn out that it's great. And the only reason I'm not using it right now is because I'm not used to it. Last week we were also struggling a little bit with it, but throughout this project we will be using it. Alright, so here selecting the columns, and then just a little bit of data wrangling, and we had this plot. So this is where we ended up last week. So as I remarked, that there were some genes that were really not very frequent. These are not going to be very interesting. Some genes that are very, very frequent, these are also not going to be very interesting. If you're a gene involved in basic machine neural life, you're not very interesting per se. But then there was still a very nice middle ground where we could explore. Alright, so today let's start by doing the same thing, but let's look at some other data sets. So let's see. Okay, so we have this. I'm going to go back to the shell. Let me just see where I am. Okay, and I am going to just let's use okay. Let's just try a couple of different other databases. For example, okay, first of all, I now see we have two versions of deep ARG. And again, this fits into this deep, sort of to this dog fooding idea, which is, okay, let's use the tools that we have, or let's use the resources that we have publicly available, but approaching them from the outside. So, for example, one of the reasons why I hadn't noticed that not all of the data was publicly available is because it was available on my laptop. And so here, when I'm being a little bit stricter with myself and saying I'm gonna only use the versions on my computer, then or that are publicly available, I immediately run into that problem. Okay, so so I'm gonna do a little bit of a detour and just compare these two files. So, okay, sorry, yeah, so sorry about, so that magic on the command line, that was really just because I need that to run GitHub Copilot. Alright, so I am going to go back, open read only. Okay, so I'm gonna be just yep, that's okay, so df0 df0 is this one and df1 is this one. Are they the same? First of all, can we do this? No, there's no attribute all. Okay. Okay, I'm literally just gonna read polars all true. Okay, right, let's see. So, okay, so this is polars compare to the difference. There's also frame equal. Okay. Okay, so they are equal. Alright, so okay, so that's great. Great news. Actually, okay, so actually, are they the same file? Okay, this was a little bit, yeah, they are the same. Yeah, okay, I could also have done this. Okay, now, this is, as I said, this is a little bit of a detour from the main, so which is, now I went into the to the ArcCompare project, and saw that there were two files that seemed to be hard to know what was what. Turns out that they are actually exactly the same, and so I am going to delete one of them, and I am going to delete this one, because this other version, the name, so if everything else is, the tool.projected.norm10m.tsv.xz, and this one was probably an early version where the naming was less consistent. So I am going to, so here I am working in the ArcCompare project as a slight detour. Okay, and okay. Oh, all right. I'll figure that out a little bit better. Okay, so let's go back to the main. Okay. And we also don't need to compare it anymore. Let's go back to. All right, let's go back to the main. which is okay. Let's try RGI strict, for example. And this one is projected and one is projection, which I also don't like, but okay. All right. So this is a little bit different. So RGI strict is the so RGI has a couple of, as I said, both RGI uses the card database and then annotates all of your genes to the card database, or annotates whatever genes you give it as input to the card database. And when we first started doing this, we noticed that there were a couple of there's this, it can annotate them either identically, right? If it finds exactly the same sequence at the amino acid level, then obviously that is what, that is the gene, right? The question is now, what happens if you find the sequence that's close enough? How do you say this is close enough? So what's the exact criterion for close enough? And there you can, I'm simplifying a little bit, but if you say you want only the strict ones, that's a little bit more, that was going to be a little bit higher confidence. Right, so in this case, you can see, right, there's this, feels more like a long tail, so there's not a lot here on this right hand side, but we see still a decent number in the middle. Alright, and okay. Okay, I'm sorry, I'm going to go, okay, I'm doing a little bit of a chaos monkey type thing here, but this was a little bit annoying me. I'm just so now in the rcompare, all of the files really do have the name, tool.projected.norm10m.tsv.xz, and so in the norm10m, I think I mentioned this in passing last week, so these things have been normalized, so it's as if there were 10 million reads. So let's see. Sorry, normally I work, and here I thought it was going to be helpful to have, to not have a big, what do you call this, like prompt? Yes, you don't have a long prompt, but now it's actually not great because I also don't see where I am. Okay, so that. I'm really just playing around with the data for now a little bit. So tools. Okay, so here I'm using NeoVim, but this is actually traditional Vim, which is you can write yourself a little script by typing Q and then a letter. So now this is going to be the script W, and then if it does something like, sorry, just popping I'm gonna start so recording W, and then let's say inserts hello world, and then goes to the next line, and then Q to end, and now FW reproduces that. It's not really very interesting in this case, but you can be a little bit more like these little things like, okay, for each of these lines just indent it and put a string quote, open quote, and then comma at the end. This works very well. Okay, works very well. So so we have here the tools. Let's see. So there's 9 of them. So sorry. So let's do, yeah. Okay. All right. So this was actually pretty good. I think this is correct what I wanted to do. Oh, okay. Okay, I need to go fix the. Okay, so let's do this. Okay, so here I'm just going to redo it with share x equals and true and share y equals true, so that this way the axes are aligned. So it makes it slightly easier. And then so I actually didn't even double check because this was the code that GitHub Copilot wrote, but in this case it's actually, so if you use GitHub Copilot, you start to learn a little bit when it is trustworthy, and this type of situation where you are really it's really just asking it to adapt something that's just there in a it's actually really good. So in this case, all of this code was already there. It was just not inside the loop, and so since I had the code there for it to see, and then I just said, okay, I'm going to do a loop here. It immediately figures out. Okay. Okay, let's just look at this. Okay, so okay, so yeah, let me okay, this is a little bit better. Yeah, so here what I did is I just set the y scale to be a logarithmic scale. So alright, Okay, so here the way to read this is that the title is on top. They're a little bit all on top of each other, which I don't particularly like. Okay, so, but yeah. All right. Anyway, obviously, if this was being done for publication, we would spend a lot more time now figuring out how to make it look not ugly. But since this is now being done uniquely for us to understand the data a little bit, it being ugly is actually quite okay. Right. So all. So almost all of these curves follow this kind of long tail distribution where there's a peak on the left corresponding to rare genes. So that was one of the findings of the GMGC papers, that most genes are rare, and this is a surprisingly robust conclusion to different definitions of the word gene. So most unigenes are rare, which is one definition of what we mean by gene, but most genes in the family, shared ancestry are rare and intermediate. So in here, apparently most antibiotic resistant genes are rare, except with deep ARG, where it's a little bit of a flatter curve. It's and actually so if I compare here RGI and RGI strict, I actually had to look a couple of times back and forth because the curves looked so similar that I thought maybe there was some sort of confusion there, but no, there are some slight differences. That part there, this area here, does look a little bit different when you look closely. So interestingly, and this is actually going a little bit on a tangent, but so Abricate Card and RGI, they use the same underlying database, but the results with Abricate are very, very different. So Abricate is maybe the word would be more conservative, so it's not going to be outputting as much. All right. So this is interesting. All right, so okay, I'm gonna save this. So one of the issues here is that so far we are just putting everything in the same bucket. We're just counting how often things appear in the same metagenome. But since the GMGC uses is the first G stands for global, so we have a lot of different habitats here, and so eventually it would be nice to check whether there's something, this could be a confounding effect, because if two things go together, if two things happen to be present in a certain habitat, they will go together because that's a habitat effect. So we would want to remove that, or at least be aware of it. So maybe we can do that now. Maybe we can, yeah, let's do that now. Okay, so all right, let Jim. Okay, so for that, what I'm going to do is I am going to I should organize this a little bit better. Okay, I'm going to go and get the data for the GMGC, and I could do this by going to the website. little bit. Not sure why it's slow. Oh yeah, I can go here, go to the website, downloads. I'm gonna post this in the chat. Could go to the website, downloads, and yeah, and I could get this, or I can go here to the and then what I will be looking for is this metadata, sample metadata. Okay, and so this is what I did. I cloned it and as I said, this if you are doing this for yourself, it might be simpler to just download from the website, but otherwise, if you are familiar with Git Annex, which is it's actually quite nice, and it's quite nice, and in this case, I got this data. All right, so this is actually the repository. I am just going to be writing here data, genomes, and okay, let's update this. Okay, so let's update the notes that we have. All right, so this was okay, so let me just see what did we do. We did this. Alright, so I'm just writing down what we have, what I was just saying. So the data, I mean everything is here online, is available here. Up here, but also okay, and using Git Annex. Okay, and Git Annex, it's also going to link to it. Okay, Git Annex, it's, let me put it this way, it's far from trivial to use the first time. It's incredibly powerful. I mean, a little bit like Git itself, which is, it's incredibly powerful and flexible, and it makes absolutely it never sacrifices flexibility and power for usability, which means that you can use it to do more or less whatever you want in its domain, but it's maybe not trivial if you haven't used it before. But it's really incredibly flexible and powerful, and it can do all sorts of things. But if you're just using this one project and you just want to get this one file, I would probably say you should just go to the website and just download it using the web browser. Okay, so let's put Alright, so in here, I didn't say this, but right, so there's several metadata files. So some of them are related to the origin of the unigenes themselves. You know, so for example, if they come from progenomes 2, or if they come from you know, if they come from a metagenome, but what we're looking here is this sample. So this is the sample metadata. So just looking at the table here, so so there's a sample identifier, and there's actually 2 of them. So this is the public sample identifier, and in this case there was a different name internally, because this data were not, were not publicly available when we started the project. Now they are, and then here habitat, then some, it's a GC fraction. This is the size in base pairs, high quality, and then the raw, so the original inserts, the number of open reading frames, then some of the basic metadata that we used in the manuscript. Alright, so okay, so let's go back to, alright, now we got the data, and now we go back to exploring it. Okay, so so first of all, metadata. Yeah, that was not about, but it's not that, it's okay, no. Okay, I think this will work. Yeah. Okay, now, okay, that's actually not bad. Habitat equals human gut. So there's a few different ways we could do this. So the simplest one is to just select the human gut. And actually I am also going to select, but actually I'm going to be even a bit stricter. Let's say we have, sure, yeah, I'm going to select, I'm going to throw away any samples where the high quality so first of all, we're calling them inserts, and the main reason why we say insert is because, so here we mean, so if it's a paired read, so that counts as one insert, and if it's a single read, that also counts as one insert. So it's one physical piece of DNA that and we only care about the high quality ones because so this is reusing public data, and especially reusing public data, some of it going back a few years already, and so the quality standards are very what's the euphemism, they vary a lot, and to some extent this is just a function of the fact that data has gotten so much better over the years, and so in some of the older data sets you might have, even if you have a lot of inserts at the input, once we do quality filtering, which we've used, obviously this was NGLS. NGLS was actually heavily basically developed for this project, or had to be heavily adapted for this project at the very least. It was we with the older samples we end up discarding a lot of reads when we do the quality control, whereas with newer samples we end up keeping almost all of them. So the correlation between the initial number inserts and the final one is not really very strong. Alright, so and then okay, we don't want to use too many. We don't want to use too many of these low abundance samples, because they would just potentially be noise. Okay, right. So now we have. Okay, now I want to. So now we have. Okay, now here I have. Okay, these are the samples I want. Sample ID, and how do I use this to filter out? Is this something that exists? Nope. Alright, okay, back to Googling how to do things in polars. Polar select is in. Okay, is in. Is underscore in. Okay, this is very good. Okay, let's clean up here a bit. Okay, right, so here, okay, first of all, cleaned up there a little bit. So I'm not a particularly big fan of these hard rules about how wide your lines should be. You know, I think this, especially with Python, because anyway you're using indentation, right? So here, if you're starting, or even here below, right? If your logical line starts, you know, with 12 or even more spaces, then then I think humanly we don't actually perceive that as 12 units of complexity, and so nonetheless, it's also there's something real in the sense that we should not have things that are too complex. Okay, so this is good. So what I'm trying to say is I think that it's good to keep complexity down. So each individual line shouldn't be overly complex, but these hard rules about don't make your lines longer than 80 characters, I think that's not capturing the right thing. I think that's capturing basically how a lot of that is still how wide terminals were in the 1970s, or how wide punch cards were, and then we kept those heuristics because we do want to keep complexity down, but we should somehow update them to to some fuzzier notion. Okay. Right. So having said all of this, let's go back and let's just do this. Okay. Let's run this again. Okay, I'm not sure that this is the right version. No. Okay, I'm gonna do this from scratch because I'm not sure which version is what anymore. Oh, okay, there was some error. skip this for now. Alright, let's having skipped that for now. Right, so these are the same results as previously, but now only looking at the human gut. Alright, so again, RGI here at the bottom. Both of these are almost identical, but again, if you look closely, need to look closely. But again, we see this sort of long tail distribution where on the leftmost side we have high frequency and then going down more or less linearly in a log scale. Especially if we ignore the first bar, which is 0, right? So that bar could potentially be as high as it could. So those are the genes that we never see. Right, and all right, let's figure out what went wrong with deep ARG. Right. So this is fine, and then this here. Okay, so this is okay, so deep ARG does not have okay, so let's see data. Okay, so so it's so these are always sort of minor things that end up. Okay, so it seems that all of the files except the ARG have the first column is called sample, and then deep ARG the first column has no name. Is this it? Alright, so let's go back to it. Does this work? Okay, colors. Work? No. Okay, this works. Okay, so we need to rename using this. This works. And then this works. Okay, so let's special case this. Work. Okay. Alright, okay, now going back to the outputs. everything, yeah, looks as expected. So again, the deep ARG result is a little bit flatter than all of the other ones. Okay, so I'm not a particularly big fan of this solution for now, but for now it will do. So ideally, and maybe that I'll do offline, I'll go back to the ARC compare and figure out why this deep ARG looks different. And actually, if I had to guess, I would say we probably did deep ARG before we did any of the other ones, and then we didn't go back and fix that. You know, we also already saw that, you know, the naming of the files was slightly off. Okay, having said all of that, I'm now let's wrap this up. Let's wrap this up. So let's see. What did we do? Okay, let's. I'm going to. Okay, this is good. Okay, so that's that. And so I actually do like to just go over, so this is also one of the nice things about Git, in my opinion, is, you know, I was just playing around with the code without really paying attention, but now at the very end you can go back and sort of make a more informed decision about what of this code do I want to keep, what is, you know, what was, you know, an interesting exploration, but, you know, not really relevant, and what's what. Okay, so in this case, yeah, I think this all makes sense. So okay, so I'm gonna commit it out. I'm gonna commit it as well. Export. Okay, and I'm gonna push, and yep, and then okay, so then offline I am going to fix. Oh, there it is. I'm going to fix the art compare. So the changes I made here, I'm also going to be pushing them to that repository. There's some, there were just some authentication issues there, and I will then also record the recap video very quickly, and I will. I also said I'm going to post the NeoVim, you know, for whoever wants to also have a look, setup that I use. It's a plugin. Yeah, with that, now we're right on the dot. So I am going to end the stream and log off, and I will see you all next week.